Hello, my team. Are you ready for the last leg of our journey for the semester? Last video. Oh, I know you guys are excited. I hope you're sad because you're going to miss me. All right, anyway. Polyprotic acid titrations. I'm not going to look at polyprotic bases, but we will look at polyprotic acids. And I'm just going to look at it from a qualitative point of view. I think I've inundated you with enough math. So this is what lucky video number 13 in this journey on buffers and titrations. So we did all the strong acid, strong base, weak acid, strong base, weak base, strong acid. We did all those calculations, every point along those titration curves. Now we can just kind of sit back, think about what we've learned. We could do these, but they take a long time to do, because polyprotic acids have multiple acidic hydrogens. So if we add, of course, we've looked at them before. When they're in water, they ionize in successive steps. And I think if the second Ka was really, really small compared to the first one, we could kind of ignore the contribution of hydronium from the second step and treat them as like pseudo-monoprotic acids and calculate pHs. That was all fine and dandy. But when we're neutralizing, we can't ignore the second step, because you're probably going to titrate them with a strong base. That strong base is greedy. Oh, it's going to take all the acidic hydrogens. I'll take you and I'll take you. Thank you very much. So if we have any polyprotic acids, and again, how do you know? Well, if you look on, you just look for the number of acidic hydrogens. Well, you see here that has 3 acidic hydrogens it could take. That has 2. This has 3. So you can just look through on any one of these, and they got multiple Ka values. And each successive Ka value gets very small. So Ka1, Ka2. What we're going to do is we're going to make a similar assumption for qualitative examples that I could ask you. If the first Ka, for example, let's take, was that selenous acid, something like that, H2SeO3. Let's see if we can find that on our trusty, you thought you were done with these tables, didn't you? So there's selenic acid, H2SeO4. Selenous acid is H2SeO3. So Ka1 is 2.3 times 10 minus 3. That's pretty big. Ka2, the second hydrogen, is 5.4 times 10 minus 9. Wow, that's almost a million-fold smaller. Woo! We're going to use a similar kind of assumption or trend. If the second Ka is at least 1,000 times smaller than the first Ka, we can make an assumption that the neutralization, if we add a strong base, will happen in distinct successive steps, which would be visible on a titration curve. So we're going to see something where that if, like I said, if the Ka1 value is more than 1,000 times bigger than Ka2, we'll see what appears to be a monoprotic acid titration curve. So you'll see it come up and boom! You'll see that first equivalence point when this first titration happens. So the strong base takes off the first hydrogen, right? Ending up with water, and then you get the sodium salt of, in this case, the conjugate base, HSeO3. So you'd see it initially and it'd go wham, like that. Normally, we'd be done with a monoprotic acid, and it would just tail off. But we have a second one, so you're going to see it go boom, and then the second neutralization happens, so you see it go boom, and then boom. You see 2 distinct equivalent points at different pHs. And we'll look briefly at why they occur at different pHs. The initial pH, we just do like we would normally do any acid, assuming the second ionization step doesn't produce enough hydronium to matter. And then this one we just treat like any other problem. See, the sodium doesn't do anything, so the HSeO3 minus would be the species that exists at equilibrium. The problem is they're amphiprotic. Oh no! So we have to do Ka versus Kb. We'll look at that briefly. You can review some videos on amphiprotic species if you want to. That would help a little bit. But once that's fully neutralized, then that comes down, and that last acidic hydrogen's taken out to give you water, and then the sodium salt of the selenite ion, SeO3 2 minus. And then the second equivalence point would just have the SeO3 2 minus and sodium. Sodium's neutral, so we'd have to look at the Ka versus the Kb. Turns out that doesn't have a Ka value, it'd be just Kb. So the initial pH is going to be pretty low. The second pH, well, we'd have to look at Ka versus Kb and see if it's in above or below 7. And then the last one, that'll definitely be up above 7. That'd be basic. So let's briefly look at that and then draw kind of a generic one. I'm not going to make you do any calculations. Just think about the concepts involved. So let's erase this and let's look at the species that exist at equilibrium. They exist after they've been neutralized at the equivalence point, and then we just take them forming an equilibrium with water. And how do we calculate those pHs? Just to get a rough estimate of the pHs at the 2 successive equivalence points. If it was triprotic like phosphoric acid, you're going to get 3 of them. Oh man, gets crazy. All right, gets kind of fun looking at them. Can you see the 2 successive equivalent points there with them rising up? So this would be, I just did some rough calculations. I could have, but I didn't want to. This is the last video. I was done doing calculations. I didn't want to spend 2 videos on this. So I'm just making it qualitative. I took about 25 milliliters of 0.1 molar selenous acid, titrated by 0.1 molar sodium hydroxide. Made the numbers easy on myself. I just did some rough calculations, fairly accurate. And I just started with the original weak diprotic acid, assuming, and it's safe to say the second ionization we could just ignore, so we just take the hydronium from the first one with that concentration. And the Ka value was, for selenous acid, 2.3 times 10 to the minus 3. So that's not a strong acid, but it's a pretty mighty weak acid right there. So I got an initial pH of around 1.8. We haven't added any sodium hydroxide yet. Same calculation as we would do for any weak acid, okay? Set up the ice table, all that fun stuff. And we start adding sodium hydroxide, and if they're the same concentration, it would require the same same volume. So 25 milliliters would be the first equivalence point when the sodium hydroxide peels off that first hydrogen ion. And since the Ka2 is times 1,000 is still smaller than Ka1, this is going to happen in 2 distinct steps. We'd see them. And if you did this in a lab, wouldn't this kind of, if you didn't know it was a polyprotic acid, wouldn't this kind of tell you something weird's happening here? Why are we getting 2 distinct equivalence points? Maybe it's got 2 distinct acidic hydrogens, right? You can do a titration of an unknown acid. It'll tell you real quick whether it's monoprotic or polyprotic. Do you see 1 equivalence point or multiple ones? So at the first equivalence point, right, the H2SeO3 is gone. All we have left is the HSeO3 minus. The problem with that is HSeO3 minus is amphiprotic. Oh man, you thought you were done with this stuff, didn't you? So if you look back in another chapter on equilibrium, we did polyprotic acids, ions, whether ions are acidic or basic, and we looked at amphiprotic species. And to tell whether an amphiprotic species is going to act like an acid or a base, you have to do the Ka versus Kb. Okay? So in this one, Ka is greater than Kb. I'm not going to go through and do the calculations. I did just to make sure. We know Ka for that because we can look at it. For HSeO3 minus, that's a 5.4 times 10 to the minus 9. See that? So if you want to do the Kb, you just take Kw divided by the Ka of what it forms, which is H2SeO3. So you take 1 times 10 to the minus 14th divided by 2.3 times 10 minus 3. That's going to give you a really tiny number. So Kb is going to be smaller than Ka. What that tells us, if I have a solution of HSeO3, and you can calculate the concentration, figure out the millimoles formed, 25 plus 25 divided by 50 milliliters, you'll get a concentration, set up an ice table for HSeO3 as an acid, because Ka is greater than Kb. So in this case, the first equivalence point should be at a pH lower than 7. And when I calculated it, I got about 4.8. Happened right at 25. Right? So if you're doing a generic titration curve, you won't need specific pH values. But you could kind of do a rough calculation, do Ka. That only takes you a few seconds, because you can look up one and solve for the other. And just compare them and it'll let you know whether the pH is going to be below 7 or above 7. But maybe not exactly where it's going to be. All right, once that first H plus has been neutralized. Now we've got the HSCO3 minus, really the sodium salt of that. And now we start adding the sodium hydroxide, and it starts pulling off the second hydrogen, so you get that second neutralization step. But it's got a really low Ka value, right? 10 to the minus 9. Once it's all pulled off, and that'll be at the next 25 milliliters, right? So it took 25 milliliters to neutralize the first one if they're the same concentration. So it'll take 25 milliliters to neutralize the second one. So at 50 milliliters, double the first one, we get the second equivalence point. If we had a third one, it would happen at 75. But we don't have a third one, right? Maybe if we had, H3PO4 or something. So at 50 milliliters in this case, or twice that volume, we get SeO32 minus. Now that doesn't have an acidic hydrogen to give. There is no Ka value. So SeO32 minus is basic, right? We don't know what its Kb is, but we could solve for it. Kb would be Kw over Ka of HSeO3 minus. Right? When I did that, and I set up an ice table, so I figured out the concentration of that. I took the millimoles form divided by the total volume, which if you think about it would be 75. 25 for the acid, 25 to hit the first equivalence, and 25 for the second, so you're dividing it by 75 milliliters. You could do it, if you're curious, if you're bored, got nothing to do, no hot dates on a Saturday night, no restaurants open, no movie theaters to go to, no gym to go to. You got time. You could do this and see if you match my numbers. I'd be impressed. Figure out its concentration, set up an ice table for that as a base. All right. Forming OH minus, you get POH, sulfur X, and that'd be OH minus, get POH subtracted from 14. I got about 10.4-ish. All right, 10.4-ish. And then after that, it would just gradually rise because you have leftover strong base, so it would rise up towards 13-ish probably. The key thing is you can see the two distinct steps, and they have like if you took a strong acid, strong base, you'd have this huge rise here. Monoprotic one like this. You get these diprotic ones, you get these tiny little things here. So you get this very, very small spread of where you could pick an indicator. I mean, there might be one indicator that really, really works, right? So this is 1, 2, 3, 4. I mean, you're good between maybe 4 to 6 on this one. So if you're looking at indicator tables between 4 and 6, you don't have too many options, right? So if I'm looking for an indicator for that first equivalence point between pH 4 and 6 right here, maybe bromocresol green, methyl red, something like that. Options are limited. And for the second one, right, we need a separate indicator. So we're talking 7, 8, 9, 10, between 9 and 11, maybe, if we're lucky. So if we're looking between pH 9 and 11, you're looking at, thymolphthalein, maybe phenolphthalein over here. Those are some good ones because they're colorless to color. It'd be fun to use one other than phenolphthalein. We're so used to colorless to pink. A lot of students think we always get colorless to pink. And then if you do a titration, you're like, whoa, using a different indicator, it freaks some students out, right? I've actually had some colorblind students who couldn't see the color of phenolphthalein. So I just went and created or found other indicators that worked for the pH of that particular titration. And I'm like, can you see this color, see this color? And hey, rock and roll. You could figure everything out. And it was kind of cool because all the other students like, whoa, I wish my titration turned blue at my endpoint. So we just had fun with it, right? But you get the basic idea. Just look at the species that exists at the first equivalence point. It's an amphiprotic species. Compare Ka to Kb. Whichever one's bigger determines whether it's going to be acidic or basic, below 7 or above 7 at the equivalence point. And you could calculate it if you want to. And then the second one, if it's a diprotic acid, right, it doesn't have a hydrogen, so it can't have a Ka. It's a Kb only. If it's a triprotic acid, that would also be amphiprotic. Most likely Kb would be bigger than Ka. But you just never know till you try it. Polyprotic acids, and you can do the same thing with base. You just start up here, and then you'd have the two, coming down. but I'm not going to worry about those. So a couple of these on the homework. I'm not going to make you calculate any of these on an exam. Maybe draw one, a generic one, right? If I said, hey, draw a generic titration curve, and I could pick some diprotic acid out of there, you know, neutralized by or titrated by sodium hydroxide. You can just draw it, figure out what the pH is around here real quick, compare Ka to Kb. You're good to go. It's been a pleasure, my friends. Enjoy and study hard.